One of the most important concepts we need for this course is the concept of vectors. In this video, we will explain what vectors are and some of the basic vector operations we'll use as we get started with kinematics. A vector is any quantity that has both size and direction. For instance, if I say I drive 5 miles on Route 9, that isn't a vector because I didn't specify a direction. A quantity that has only a size is called a scalar. On the other hand, if I say I traveled 5 miles east on Route 9, that is a vector. Most quantities in physics are vectors. We have to account for both their size and direction. Now, let's see how to specify vectors. Here, we see a log stretched out over a pond. It is oriented exactly east-west. You look out and see a shark. How would you describe where the shark is relative to you? There are two ways, and we will look at both. Here is one way to locate the shark. The shark, as we can see, is at this point over here. We could locate the shark exactly and unambiguously by stating how far the shark is east of our position, which is at the origin, and how far north of our position. Let's start with east. So from the looks of it, the shark is located at 12 meters to the east of my position. Remember, I'm at the origin. I'm always at the origin. So that would be 12 meters east of me. And the shark is located, that looks like 16 meters north of me. So that means that I have now unambiguously stated where the shark is relative to myself. The shark is in this overall direction. We can represent the sum of those two components, or those two contributions, the east contribution and the north contribution, as one single vector, like this. And now we have located the shark. The shark is located 12 meters to my east, 16 meters to my north. And the most common way to write that as a vector is like this. 12 I hat, to symbolize the fact that this is in the east, or equivalently the x direction, plus 16 j hat to symbolize the north, or equivalently the y direction. This system is called the rectangular notation for vectors. In rectangular notation, we put the initial point of the vector at the origin. The vector is identified by the x and y components of its terminal point. We usually use the terminology I hat to represent the x component and j hat to represent the y component. As you probably guessed, rectangular notation can easily be expanded into the third dimension, like this. In the case of a three-dimensional vector, we would account not only for the x and y components, but the z component as well. We would include a k hat term to represent the z component. But this isn't the only way to locate the shark. Here is a completely different way of finding the location of the shark. Starting from the origin, which remember is your position, let's draw a straight line that travels from you to the shark, like this. And now let's measure the length of this straight line. In this ruler over here, I can measure this out to be 20 meters. So that tells us how far away the shark is. But I don't yet know what direction it's in. For that, I will need a protractor. Now if I set my protractor here, I'll line it up at the origin and find out what is the angle at which this vector points. I get about 53 degrees. So now I have unambiguously located the shark again. I have located it at a point that is 20 meters away at an angle of 53 degrees. Unlike rectangular notation, this system uses angles as well as distances. It's called polar notation. In polar, a vector is identified by its size and its orientation. The size is generically represented with the letter r, and the angle or the orientation by the Greek letter theta. The positive x-axis is considered to be 0 degrees, and we measure all angles counterclockwise from there. So positive y is 90 degrees, negative x is 180 degrees, and so forth. There are 3D versions of polar notation, known as cylindrical and spherical coordinates, but we won't use them in this class. Rectangular and polar are like two languages. You can express the same vector in either notation, but which notation you want to use depends on what type of puzzle you're trying to solve. It's a bit like how the English sentence, "I want an apple," means the same thing as the German sentence, "Ich möchte ein Apfel." But if you visited Switzerland, where some people speak English and other people speak German, you would choose one language or the other based on whom you're talking to. And just like you can translate between English and German, you can translate between polar and rectangular. Whenever you have to convert the vector, make sure you draw it first. This is important, and we'll see why in a minute. Also, I will take off points on your homework if you don't do it. Now, let us take this coordinate, this vector, which was provided to us in polar notation, and convert it into Cartesian notation. In Cartesian notation, or rectangular notation, we are provided with two different pieces of information. A distance along x, and a distance along y. Something like this. And what we'd like to do is to find out what the x and that y value are. Here's x, here's y. Let us solve for x first. We know that x is the adjacent side of this 53-degree angle. That means if I took x and I divided it by 20, that's the length of the hypotenuse of this right triangle, then x over 20 is going to be equal to the cosine of 53 degrees. Which means that x is equal to 20 times the cosine of 53 degrees. 20 times the cosine of 53 degrees gives me 12.03, very close to 12 meters. What about for y? Well, y is the opposite side of this 53-degree angle. So that means that if I were to take y divided by 20, that would give me the sine of 53 degrees. Okay, so y is equal to 20 times the sine of 53 degrees. Once again, I'll have to use my calculator for this. 20 times the sine of 53 degrees is very close to 16 meters. So now it works out to 12 in the x direction, 16 in the y direction, which I can also write like this: 12I hat plus 16j hat. To convert from polar to rectangular, we need to find the x and y coordinates. First, we always start by drawing the vector. X is equal to r cos theta, and y is equal to r sine theta. These are the formulas required to convert a vector from polar notation to rectangular. Here is the position of the shark as before. We have expressed it in rectangular coordinates. Now we would like to turn this into polar coordinates. How do we go about doing that? Well, you might notice that the way that I have set up the relationship between the components in rectangular and the overall vector itself gives us this right-angled triangle. What is the length of this side? 12. And what is the length of this vertical side? 16. So all we have to do is to find out what is the length of this last side. And as you probably guessed, the easiest way to do that is going to be using the Pythagorean theorem. So the length of this last side, let's call that r, is going to be equal to the square root of the first side squared plus the second side squared. You can stick this in your calculator and find out what that is. So square root of 12 squared plus 16 squared, move it over here so it's a little easier to see, is equal to 20. So the length of this side is 20 meters. How about your angle, the angle of orientation? What is this angle over here? The opposite side of this angle has a length of 16, and the adjacent side has a length of 12. So if we wanted to find out the value of theta, we can tell that the opposite side over the adjacent side will give us the tangent of that angle. So all we have to do is find the arctangent of 16 over 12. Let's put that into our calculator and find out. Second, arctangent of 16 over 12 gives us 0.927. This must be in radians. Let's change that over into degrees and let's do the same calculation over. 53.13 degrees. Now, consider this situation. The shark is now located at this point, which is given to us in rectangular coordinates. Negative 12i minus 5j. Negative 12 along the x-axis, negative 5 along the y-axis. We want to find out what its polar coordinates are. So first, let us solve for the distance from the origin to the shark. We would solve this as r is equal to the square root of -12 squared plus -5 whole squared. So once again, this is just a Pythagorean theorem to find out what this distance is. You could do this with a calculator if you really wanted, but I'll just tell you that the answer is going to be 13. So this distance is 13. Now, what about the angle of orientation? We always treat the angle of orientation as starting at 0 degrees being the positive x-axis, so we are interested in this angle over here. That will uniquely place the shark. So, using the information that we're given over here, we can tell that for this small angle over here, which I have marked with 2 arcs, the opposite side is -5, and the adjacent side is -12. So that means that if I were to call this small angle theta, then theta is equal to the arctangent of -5 divided by -12. Once again, we can use our calculators to figure out what that is. The arctangent of -5 divided by -12 equals 22.62 degrees. Now, you might notice a problem here. 22.62 degrees corresponds to this angle inside the triangle. It does not equal the overall orientation of the vector, which is given by this arc over here. So how do we figure that out? We have to add 180 degrees to it. So the real value of theta is equal to 22.62 plus 180 degrees, which works out to 202.62 degrees. To convert from rectangular to polar, we always draw the vector first. We apply the Pythagorean theorem to get r. r equals the square root of x squared plus y squared. And to get theta, we take the arctangent of y over x. But if we see from the drawing that the vector lies in either the second or third quadrants, we have to add 180 degrees to the answer that our calculator gave for the arctangent. As I said, we won't use 3D vectors too often in this class, but if you ever need to find the size of a 3D vector, that is, to convert it from rectangular to polar, we use the three-dimensional version of the Pythagorean theorem, shown here, to do it. r equals the square root of x squared plus y squared plus z squared. Now, let's look at some vector operations. When we add up two vectors, the process for doing it is like this. We take the first vector and align it so that its tail is at the origin, as usual. We then take the second vector and align it so that its tail, its initial point, is the same as the terminal point for the first vector. Then we can just add up the corresponding rectangular coordinates for each. So the first vector has coordinates of 3i hat plus 1j hat, and the second vector has coordinates of 1i hat plus 4j hat. So the sum of these two is 3 plus 1 is 4i hat, 1 plus 4 is 5j hat. What does that mean? It means that if we were to trace a new vector that starts from the initial point of the first vector and travels all the way to the terminal point of the second vector, like this, then in Cartesian coordinates or rectangular coordinates, the equation or the coordinates of this new vector would be 4i hat plus 5j hat. This is how addition of vectors is done. Supposing I added on a third vector that points like this. Let us say that this third vector has coordinates of negative 10i plus 2j. In that case, we could add this new vector to the resultant of the first two and find out where this terminal point is with respect to the origin. Easy enough. 4 minus 10, that gives us negative 6i, 5 plus 2 plus 7j. In general, you can only add vectors in rectangular notation. If you're given two vectors in polar, you have to translate them into rectangular before you can add them. All you have to do is add the x components of the original vectors to find the x component of the resultant, and add the y components of the original vectors to find the y component of the resultant. If these had been three-dimensional vectors and there were z components, you would add them in the same way. Subtraction follows the same logic, except we subtract the coordinates rather than adding them. Here is a typical vector, 3i plus 4j. Let us suppose that we scale it by a factor of 2. To do this, all we need to do is write the number 2 in front of 3i plus 4j, put some parentheses, and then multiply or distribute the 2 across these two terms. So 2 times 3i, that gives us 6i hat, plus 2 times 4, that gives you 8j hat. And that's it. That's all we have to do in order to scale this vector by a factor of 2. What does the scaled vector look like? Something like this. The new vector is now twice as long as the original one, or more precisely, it has twice the size, but the orientation remains the same. What if, instead of multiplying by positive 2, we instead multiplied by negative 2? So negative 2 multiplied by 3i hat plus 4j hat. So taking the original vector, 3i hat plus 4j hat, and multiplying it by negative 2. That would give us, again, distributed in the same way, negative 6i hat minus 8j hat. What does that look like? Like this. So multiplying by a negative number takes a vector and it not only scales it, but it also flips it around by 180 degrees. What if you had to scale a vector in polar coordinates? Here we see the vector 5, 134 degrees. Let us take this vector and let us scale it by a factor of 1/5, or if you prefer, 0.2. Unlike in rectangular, where you have to multiply each term by the 0.2 or whatever your scale factor is, here you only need to multiply the size, like that. So 0.2 times 5 will give me 1, and the angle will remain unchanged. So my scaled vector over here is 1 at an angle of 134 degrees. That would look something like this. In general, scaling can be done in either rectangular or polar. In rectangular, you have to multiply each coordinate by the scale factor. In polar, you have to multiply just the size of the vector by that scale factor. Regardless of system, a scale factor bigger than 1 creates a longer vector. A scale factor between 0 and 1 creates a shorter vector. And a negative scale factor flips the direction of the vector by 180 degrees. In this video, we introduced vectors and explained how to add and scale them. These operations will be enough to get us through the first 2 topics of this course. Further vector operations will be introduced as we proceed through this course.